My name is Bun Ui. Welcome to Photonics Lab.
Hi, my name is Hassan Makin Dubai. I'm a second year PhD student here at KAUST.
And I am Aditya Prabhaswara. I'm a first year student here at KAUST. So here in Photonics Lab, we are working in things related to light, from generating light, manipulating light, and detecting light. By light, we mean that something that is generated by the LED or lasers. So for example, some of my colleagues are working in the near infrared and the telecommunication wavelength, and some of them are also working with this equipment called the molecular beam epitaxy to make visible light wavelength devices such as used in the visible light communication and flexible display.
My friend Adit and I particularly working on underwater wireless optical communication. That is, we use visible light, particularly green and blue lasers and light emitting diodes, to establish high bandwidth underwater communication system. And what we have here is a lab prototype of wireless visible light communication system. The system uses green laser and green laser diode as transmitter and avalanche photodiode as a receiver to establish communication. The oceanic underwater environment is simulated by this 1 meter water tank fitted with optical transparent window at each end and filled with seawater, and the optical light is folded by many times by mirrors on both ends to increase the optical path length. At the output, we use digital communication analyzer and high performance bit error rate analyzer to evaluate the performance of the communication system. So the motivation of our work comes from the need of reliable high-speed communication and underwater. Approximately 75% of the Earth's surface is covered with water, and there is a growing need of monitoring the oceans that is coming mostly from scientific, military, and commercial communities. Traditionally, people use acoustic, which is sound waves technology, to communicate undersea. But however, acoustic is very slow because of the speed of sound in seawater, and also is a very low bandwidth. People tried radio wave communication. However, radio wave communication also attenuate in seawater and are not reliable. And the third option is fiber optic communication, which provide high bandwidth and long ranges. However, for practical applications such as autonomous underwater vehicles, where having a wireless communication system is valuable, having a fiber optic cable from receiver to the detector and from the transmitter to the receiver is not desirable. So this is where we come in, and we use visible light to establish a communication. The most important thing here is that the seawater has a low absorption window and visible light window, and that is where we take advantage and exploit that window. Here we are mostly developing advanced modulation techniques, channel modeling, and also establishing a lab prototype that system based on visible light communication that is able to transmit gigabit signals and cover high range in seawater.
My name is Pawan Mishra. Here at Photonics Lab, we work on molecular beam epitaxy growth of denitride devices like LEDs and laser diodes. Let me describe this instrument very briefly. This is ultra high vacuum technology, and we grow devices like LEDs and laser diodes with this molecular beam epitaxy, which can be, such devices can be utilized for solid state lighting as well as optical communication, like one of my colleagues Hassan have described you.
My research here as a PhD student in the Photonics Lab in KAUST is mainly towards nanotechnology. What's very interesting about nanotechnology is that once you scale down the materials, their properties they change dramatically. That basically it's as if you are having a new set of materials. So for example, if you have like a piece of gold, it's yellowish and it's very inert material. However, if you scale it down to the nanoscale, it becomes reddish and it becomes a very active metal. What is even more interesting in the nanoscale is that once you scale down the material, the new material properties that appear, they are not only dependent on the material, but they're also dependent on the size and the surface. And thus, we can engineer the size and the surface in order to change these properties, and thus we can change the material in ways that were not possible before, so that we can address new sets of applications. My work here is that I prepare extremely thin sheets of materials that are roughly like 1,000 times thinner than the human hair, and then I study their optical and thermal properties. And then the fun part is that I actually can, through engineering the strain of the material, of the nanostructure, and the surface, and the chemistry, and the size, we can actually change the properties of these nano sheets in ways that suits different applications. The applications, they range from like biological sensors and chemical sensors and biological transplants, all the way to like flexible displays and flexible electronics, and they can also be used in thermoelectrics to generate the electrical power.
Hi, my name is Abdullah. I'm a senior PhD student in Professor Boon's group. I'm working on ultraviolet lighting applications, and we are using this material called aluminum gallium nitride to achieve these short wavelengths. Now, the current state of the art LEDs or lasers based on this material system have only achieved efficiencies up to 14%. So there is a big room of improvement which we can achieve. Now, the technique we are using in our lab is called molecular beam epitaxy to grow this material, which can have very high quality crystal structure and in a very high purity environment, through which we can achieve high efficiencies. If you look at the current market for different applications in the ultraviolet, for example, water cleaning, environmental cleaning, or vitamin D formation, people are mainly using ultraviolet lamps based on mercury. We know that mercury is a poisonous material, and the devices made using this material are not reliable, they are expensive, and the lifetime is quite short. So this provides the motivation to have a lighting source based on solid state, which can be energy efficient, environmental friendly, and reliable. Thank you. As an experimentalist, the thing which to me looks unique about KAUST are the state-of-the-art lab facilities.
KAUST is unique because of the amount of resources we have, which basically enable creative research.